This lecture will concern Galileo and the new astronomy. Astronomy held a favored place in the thought of the Aristotelian scholastics who dominated the European universities at the dawn of the 17th century. The scholastics divided the world between that above the moon, the celestial heavens, close to God, where things were perfect and unchanging, and the sublunar world, the world below the moon, where nothing was constant, where the elements were all mixed, where things changed, composed, decomposed, and recomposed. The astronomy that the scholastics had inherited from the ancients that fit this model wonderfully was the astronomy of the ancient Greek philosopher Ptolemy, which seemed wonderfully consistent with their philosophical and theological system. Ptolemaic astronomy held that the Earth was at the center of the universe. The moon, the planets, the sun, and an orb of fixed stars revolved around the Earth in perfect, unchanging, circular motion. What made the Earth's position dramatic at the center of the universe was not that that was a privileged place, but that this was the farthest remove from God. And the goal of life and astronomy reinforced this, was to move from the corrupt, changing world below the moon to the eternal, unchanging heavens close to God. Among the intellectual movements that arose in early modern Europe, above all in the 15th and 16th and 17th centuries, to challenge the dominant Aristotelian scholasticism was what we term Neo-Pythagorean thought, a revival of the thought of the ancient Greek mathematician and mystic Pythagoras, where the Aristotelians and scholastics viewed the universe in terms of its perfections and its purposes, qualitatively. The Neo-Pythagoreans viewed the universe quantitatively, in terms of mathematics and geometry. The worldview of Aristotelian scholasticism expressed the conception that all things had a particular essence that made it uniquely what it was, and that this essence had to do with perfections, things shared with God and the higher qualities. And all things moved with a purpose that reflected that essence. Base things, such as earth and flesh, fell toward the center of the earth. Nobler things, such as fire, that could purge material things, that could purge flesh, these rose toward the heavens. And everything moved to express its qualities and its purposes. For the Neo-Pythagoreans, the divine mind, God, expressed itself in terms of the order, the harmonies, the ratios, the mathematics of the creation. Reality emanated from the mind of the divinity itself, and it was numerical and geometrical. The Pythagoreans had worshipped the sun. The Neo-Pythagoreans saw the sun bright, luminous, perfectly circular, as an emblem of the divinity itself. One of the most remarkable thinkers in the history of European thought, and a figure foundational to the emergence of early modern science was Johannes Kepler, who was as much an astrologer as an astronomer, who was a numbers mystic, who was always looking for the quantitative, not the qualitative expression of the divine mind in reality. And he reveals to us the fusion at the birth of early modern astronomy and physics of Neo-Pythagorean numerical mysticism on the one hand, and a natural philosophy that would demonstrate the extraordinary fruitfulness of a quantitative science to the West. Kepler inherited the work of the 16th century Polish astronomer Copernicus, whose attempts to reform the calendar had led him to devise, in a system that was suppressed and that was offered to the world simply as a model by which one could do calculations, not a true picture of reality, though Copernicus himself believed that it was a true picture of reality, a universe in which the sun, not the earth, was at the center of the universe. And Kepler was profoundly drawn to Copernicus's unproven heliocentric hypothesis. Heliocentric, the sun at the center of the universe. Kepler believed that with the sun at the rightful center of the universe, the quantitative and geometrical harmonies and ratios of God's creation would be disclosed to the human mind. Inheriting the data of the Danish astronomer Tycho Brahe, that was more accurate than any astronomical observations thus made, and convinced that Copernicus was correct, that the luminous circular sun was at the center of the system, Kepler went through an ordeal of mathematical hard labor, working only with algebra and with geometry, analytic geometry, and the calculus had not yet been devised. And after years and years of calculations, often spending more than 1 year on the orbit of any given planet, Kepler arrived at his first 2 laws of planetary motion. The first held that the planets, including the Earth, described elliptic, not circular orbits around the sun. And the second proclaimed that the line joining a planet to the sun, the radial vector, swept out equal areas in equal times. Kepler now had his sun at the center of the system with ratios and harmonies consistent with his Neo-Pythagorean commitments, and he had made sense of the data of Tycho Brahe, but Kepler loathed what he saw as the imperfect ellipses, the loss of the perfect circles in the heavenly spheres. He wrote to a friend that these were, and I translate very politely, quote, a cartful of dung, end quote. And thus, for 10 more years of excruciating mathematical labor, Kepler engaged in a computational struggle to find God's harmony in this universe of ellipses. Some extraordinary order alone could justify the ellipses in God's universe. And in 1619, he found it in his third law of planetary motion, that the square of the period of the revolution of a planet is proportional to the cube of its average distance from the sun. For Kepler, it now all was worthwhile. The beauty, the glory of divine mind now was evident in the creation, introducing his third law of planetary motion in his great work on the harmony of the world. Kepler expressed himself not in terms that we are accustomed to think of in the modern age as scientific, but as follows. He wrote, "I let myself go in divine rage. I have stolen the golden vessels of the Egyptians to make a proper home for my God. If you are angry with me, I shall bear it. It does not matter if my book finds its reader in 100 years or in 1,000 years. Has not God himself awaited 6,000 years for a human mind to gaze upon his work with understanding? Has not God himself awaited 6,000 years for a mind to gaze upon his work with understanding? One of Kepler's first ardent readers was the great Italian mathematician Galileo, Kepler's admirer, friend, and fellow astronomer. But Galileo could not accept Kepler's laws. They seemed too speculative to him. Galileo had the mathematics inherited from the Neo-Pythagoreans, but he did not have their mysticism. And the appeal of Kepler's system was not that it could be demonstrated in Galileo's view, but only that it added, if true, a certain order to the creation. But we did not know if those laws were true. Galileo, however, profoundly shared Kepler's sense that nature was to be understood quantitatively and not in terms of perfections or purposes. Galileo's method was that we could not learn from the inherited books of human beings, but must learn from God's actual creation. And that meant that natural philosophy, what we today would term science, began with induction from observation. One looked at the particulars of nature, one observed them, and one induced from the particulars general principles about the operations and nature of the world. Then the human mind had to engage in the difficult task of deducing a precise hypothesis from those principles. And since nature, not the books of man, were to be our judge, of devising an experiment that would let nature decide if one's hypothesis were correct. and to demonstrate one's conclusions in natural philosophy by means of a compelling demonstration, which for Galileo meant on the basis of observation and mathematics. Galileo perfected, to the extent that one should say he invented, the telescope that allowed the human eye to observe the heavens with degrees of magnitude undreamed of by prior observers. And the power of observation linked to mathematical proof took categorical precedence for Galileo over any presumptive authority of tradition. For example, in the scholastic system, the moon was perfectly smooth, but both from observation and seeing shadows in the craters, Galileo could infer from the data of nature that there were mountains and valleys on the moon. The sun must be perfectly circular. But sun flares, sunspots, Galileo projected on to paper, and then using triangulation and geometry showed that knowing these two lines and these two angles, one compellingly knew the angle of the third part of that triangle. And that this demonstration overcame any sense that theories that somehow had stood the test of time must be taken as correct. Galileo's most revolutionary assault upon Aristotelian scholasticism was not his Copernican astronomy, though that is what would get him in such great difficulty, but his view of reality itself, above all, his rejection of qualitative perfections in favor of quantity in the universe, and his distinction between what he termed primary and secondary qualities of the things of the world. Secondary qualities, in which category he placed almost all of the Aristotelian qualities, were not real in the objects that we described, but depended upon human perception of them. Such things as sweetness or bitterness, which the scholastics placed as qualities in the object, in the thing that we observed and experienced. For Galileo, those were the result of the effect of an object upon human senses. And sweetness, color, almost all of what we thought of as the qualities that things had in the world did not reside in the entity, but were a result of human experience and the human senses interacting with the real qualities of what was out there. What were those real qualities, the primary qualities, that truly existed apart from perception, that existed where there was no mind, no human senses to observe them? For Galileo, these qualities of the objects themselves, these primary realities of God's natural creation, were all quantitative. They were dimension, shape, mass, the measurable. What the scholastics called perfections and imperfections in things were for Galileo human projections upon a natural world that was simply quantity, mass in motion, a world to be understood in terms of mathematical law. Empirical observation, mathematical ordering, and mathematical test led us to understand the laws of motion. And that's what physics, what dynamics, what mechanics were. Not an account of perfections or purposes, but the laws of matter in motion. And motion described the relationship of bodies to time and to distance. It did not express the perfections or the purposes of things. All of these views led Galileo into the most intense struggles with the Aristotelians who dominated the hierarchy of the church and who dominated the universities of Europe. Galileo argued explicitly against Aristotle and against the principle of intellectual authority, that which has stood the test of time is true and should be accepted, that humility was accepting what the ancients believed. For Galileo, humility was accepting what God had actually written in the book of nature that was open to our gaze. Facts, Galileo argued, are determined by nature, not by men, not by books. Not even the Pope, he wrote, not even the Pope could make something that God had made a fact not a fact, or something that God had not made a fact. And indeed, he reminded the scholastics that Aristotle himself, in his theory of knowledge, had called upon human beings to begin with observation of the world and with induction, inference from observation of the world. And he always would say to his opponents, quote, "If Aristotle were here today, he would agree with me," close quote. His opponents refused to look through his telescope, saying it was flawed. It obviously created optical illusions because we always had known what was there. Galileo said Aristotle would look, and he wrote to Kepler, "I don't know if one should laugh or if one should cry." With critics of the new astronomy insisting that Copernican hypotheses, which Galileo accepted, were contradicted by Scripture, Galileo distinguished between what he termed the two revelations from God: his book of nature, which was our source of knowledge about the creation, and his book of Scripture, our source of knowledge about salvation and things beyond nature. Quoting an ancient father of the church, Galileo wrote, "Scripture does not teach us how the heavens go. It teaches us how to go to heaven." If God had intended to write a text of physics, he could have done it in an infinitely superior way to what Scripture had to say about the things of science. But God had done it in an infinitely superior way. He had given us the creation, nature, and that was where one looked. Our senses, our intellect, our reason, our ability to engage in mathematical proofs. These were gifts from God. Experience and mathematical logic were irrefutable because God's creation itself was the ultimate test of reality and human knowledge. Debating with an Aristotelian scholastic opponent, Galileo wrote that the scholastics did not know how to study what God had created in nature. He said, first you must know where to look. And we look not in the books in our libraries handed down generation to generation. We look in the book of the creation, the book of nature itself. And secondly, Galileo observed, and here the legacy of Neo-Pythagoreanism is so strong in him, and to read that book of nature, one must know its language. And its language, he wrote, is the language of line and geometry and number, without which the book of nature is indecipherable. Galileo's dogged defense of the Copernican hypothesis led him ultimately into his final difficulty with the Aristotelian scholastics who dominated the office of the Inquisition in Italy and the church and the universities in general. Galileo had been asked to write a comparison of the Ptolemaic and the Copernican world systems and to conclude that the issues were so thorny and difficult that the human mind could only rely upon the authority of the church. He wrote such a book and he made such a conclusion, but the problem was that in the hundreds of pages leading up to that conclusion, he offered demonstration after demonstration of the Copernican hypothesis and refutation after refutation of the Ptolemaic system. This led to his being summoned before the Inquisition, shown the instruments of torture, recanting his commitment to the Copernican system, and suffering a house arrest that lasted until his death, during which time, in violation of the orders placed upon him, he wrote a textbook that became the foundation of modern physics. The prosecution of Galileo by the church, which was above all within Catholicism, the persecution of the anti-Aristotelians by the Aristotelian scholastics who dominated the institutions of the church, affected both the substance and the symbolism of the new science. For example, René Descartes in Paris had just completed a manuscript called The World, whose astronomy was based upon the Copernican hypothesis. Hearing of the condemnation of Galileo, he put it in the drawer of a desk, and it was not published until after his death. The persecution also created of Galileo a powerful symbol, a martyr of the freedom to philosophize and to speculate, a martyr of the new philosophy and the new science. The persecution intimidated many, but what it could not end was the extraordinary excitement of the 17th century mind. Authors rejecting authority, believing that for the first time, as Kepler had, with proper method, the human mind was looking upon God's work for the first time with comprehension. Thank you very much.